Good morning. I am Harivish from BTech third year Electrical Department at IIT Palakkad. In this video, I am going to be presenting my project in the Digital Signal Processing course. The problem statement is to design and implement heart rate based bradycardia and tachycardia classification system. Use ECG signal with fs equals to 360 Hz and estimate heart rate using autocorrelation and assume block duration of 10 seconds. So, what is an ECG signal? Electrocardiogram, abbreviated as ECG, is a recording of the electrical activity of the heart through its cardiac cycle. It characterizes various stages in the cardiac cycle and can be observed as P wave, followed by QRS complex, followed by T wave. Now, autocorrelation of a discrete time signal x of n is defined as summation over n x of n into x of n plus k. Repeating peaks of same magnitude at delay k in the autocorrelation signal will signify that the signal x of n has repeating components in it, separated by delay k. In an ECG signal, the periodic repetition of the QRS complex represents each heartbeat. The heart rate needs to be estimated from the autocorrelation of the ECG signal. In the time interval between the highest peak at delay k equals to 0 and the highest peak in the next immediate block in the autocorrelation signal will give the time taken for a single heartbeat, which will be denoted as capital T. The heart rate is then calculated as heart rate equals 60 by T BPM. Classification of bradycardia and tachycardia. At resting conditions, the normal heart rate should be from 60 to 100 beats per minute. But when it is less than 60 beats per minute, it is called bradycardia, and when it's above 100 beats per minute, it is called tachycardia. Now let us analyze a clean ECG data. In this ECG data, this is the P wave followed by QRS complex, and this is the R peak. This is followed by T wave. When we take the autocorrelation of this ECG signal, we will observe that there are multiple peaks repeating at a regular interval. This indicates the periodic repetition of the QRS complex. Along with this, there are multiple smaller peaks which are resulting due to the P wave and T wave followed before and after of the QRS complex. We need to find the time interval between these two major peaks and average it for these two peaks to get the time taken for a single heartbeat. Now, these peaks are located and marked as red dots by first thresholding the autocorrelation signal, and here the threshold is taken as 0.3 magnitude, and then finding the first order derivative of this thresholded autocorrelation, and then finding the peaks from the zero crossings in the first order derivative. Now, the average time between the red peaks is estimated as capital T equals to 1.3292 seconds. The heart rate is thus calculated as heart rate equals 60 by T, and the value is calculated as 45 BPM. Since the heart rate is less than 60, the analyzed clean ECG signal is classified to have bradycardia. Next, we will analyze the noisy ECG data. This noisy ECG data is plotted in this figure. Next, we plot the autocorrelation of this noisy ECG data. If we zoom in, we can observe that in each of these peaks, there are multiple local minimas, and when we try to detect the peaks, these all local minimas will also be detected, resulting in a bunch of local minimas clubbed together. We can see this in this figure. Now, apart from the peaks of our interest, there are also multiple local maximas that are being detected. Now, these local maximas are removed by selecting the highest local maxima in each of these paired local maximas, and the result is plotted as here. Now we will find that average of the time interval between these red peaks, successive red peaks, and consider that as the time required for a single heartbeat. And that is estimated as 1.0042 seconds, which gives a heart rate of 60 BPM. The heart rate is estimated at 60 BPM, and hence the analyzed noisy ECG signal is classified to have neither bradycardia nor tachycardia. The heart rate is normal. Now let us analyze the code. First, we load all the necessary data. Then we pass this ECG signal through a high pass filter with a very low cutoff frequency. This is to remove any baseline variations if present in the ECG signal. This will cause issues when calculating the autocorrelation. So the baseline variations are removed. Next, we find the autocorrelation from the code from 922 till 927. Next, we normalize the autocorrelation to a value of 1 and plot the data in each step. Next, here we find the thresholded autocorrelation signal with a threshold of 0.3 magnitude. This 0.3 magnitude was chosen arbitrarily to ensure minimum number of peaks selected. Next, we need to select each individual peak from this thresholded autocorrelation signal. So we do that from the code in lines from 50 till 57. We check when the positive first order derivative is taken in line 49, and then we check when the derivative changes from positive to negative. But this leads to the issue of local maxima, as we discussed before, also being directed as the peaks. So in order to remove that, what I do is first we will initialize the first local maxima as a unique peak, then consider the next local maxima, and if it is separated by 0.4 seconds, this 0.4 second value is also chosen from visual inspection of the autocorrelation function. And if they are separated by 0.4 seconds, those two are considered to be unique. And if not, then those two are considered to be bunched together, and the maximum of those two will be selected as the unique peak. And after this, we get the highest peaks of interest. Next, we find the time period of the heartbeat, of single heartbeat, by taking the time difference of the successive peaks and taking the average of them. From that, we can calculate the heart rate as 60 by time taken for one heartbeat. Then we will classify the ECG signal as bradycardia, tachycardia, or having normal heart rate. Next, what are the challenges? False alarms are one of the most important challenges in the classification of biomedical conditions that could lead to unnecessary problems for the user. Energy efficient implementation of these classification systems on wearable devices for continuous monitoring is also a challenging task. Now, conclusion. Autocorrelation can be used to detect the periodic nature present in the signal and can work even when noise is present. The heart rate determined from autocorrelation can be used to classify bradycardia and tachycardia conditions. This detection of tachycardia from ECG or PPG signal can be used in forecasting the occurrence of ventricular fibrillation. Ventricular fibrillation is a dangerous and life-threatening condition which could be caused by ventricular tachycardia. Ventricular tachycardia can also lead to cardiac arrest. So, by detecting tachycardia present in the measured ECG or PPG signal from the real-time continuous monitoring from a wearable device, a cardiac arrest can be forecasted and the users can be intimated in advance that could save lives. An example for such an incident was a couple of years ago when an Apple Watch intimated the user that the user was having abnormally high heart rates during his sleep. Consequently, when the user reached hospital and later he was diagnosed with a cardiac arrest occurring, and then a proper treatment was given which saved his life. Thank you.